Hey everyone, and welcome back to the deep dive. Sometimes in this world of cutting-edge tech, we get so caught up in the latest buzzwords, right? These groundbreaking, complex models. And sometimes we forget the profound power of, well, simplicity. Today we're going to take a deep dive into some algorithms that are, in many ways, pretty straightforward in their basic logic. Yet they remain incredibly effective, really practical, and surprisingly competitive even now. We're talking about decision trees and their brilliant extensions, ensemble learning.
That's absolutely right. Yeah, our mission today is really to unpack how these foundational algorithms work. We'll start from, the elegant way a single decision tree carves up data, which is quite intuitive. Then we'll explore how combining many of these, often called weak learners, through ensemble methods like random forests and boosting, how that dramatically improves their accuracy and robustness, makes them much stronger. And we'll definitely dig into why these methods, despite all the triumphs of deep learning recently, why they continue to be just invaluable tools for data scientists and how they still compete, very much so, with deep learning today.
Exactly. So if you've ever wondered how AI makes decisions, maybe decisions you can actually follow and understand, or how seemingly simple rules like if this, then that can lead to incredibly powerful predictions, well, you're in for some serious aha moments today. We'll see how these techniques were not just effective, but really helped democratize machine learning in a way, making powerful models accessible, understandable. So let's unpack this. Okay, let's start right at the beginning. The foundation. Before we get into all the fancy ensemble stuff, what exactly is a decision tree? I think, like, many of us already sort of get the concept because we use these decision processes all the time, right?
Yeah.
In daily life.
Indeed, yeah, that analogy is spot on. A decision tree is, at its core, it's a flowchart-like structure. It's built for making decisions. Each internal node in this tree, think of it as representing a test, a question about some attribute in your data.
Right.
Like, is age over 35? Exactly. And each branch coming off that node represents the outcome of that test. So yes or no, greater than or less than or equal to. And then eventually you follow these branches down and you hit a leaf node. And that leaf node gives you the final answer, a class label, like subscribe or don't subscribe, or maybe a numerical value if it's regression. It really is like playing a very systematic game of 20 questions with your data set.
Okay, playing 20 questions with data. I
Yeah.
like that. So how does it actually work? How does it split the data?
Right. The core mechanism is this recursive splitting. Imagine you've got that customer data trying to predict subscriptions. The tree might first ask, is the customer's age greater than 35? If yes, that group goes down one path. If no, they go down another. The simple condition, mathematically, you might see it as x of e, where x is the feature, v is the value. It partitions the training examples. It splits them into subgroups. And the goal of each split is to make the resulting groups, the child nodes, more pure than the group you started with.
Pure. What does pure mean in this context?
Pure means more homogeneous with respect to the thing you're trying to predict. So if you're predicting subscriptions, a pure group would be one where almost everyone either did subscribe or almost everyone didn't. The split tries to separate the subscribers from the non-subscribers more cleanly.
Okay, that makes sense. But how does it pick the best question, the best feature and the best value, like that 35 for age? It can't just be random, right?
No, definitely not random. That's where the cleverness comes in. For features that have an order, like numbers, age, income, temperature, whatever, the process is quite systematic. The sources describe how you can find a good cut value. You sort the examples based on that feature's value. Then the algorithm effectively sweeps through these sorted values, testing potential split points between them. And the goal is always to find the split that best separates the data according to some statistical criterion.
A statistical criterion, like what? How does it measure best?
Good question. For classification tasks, common criteria are things like Gini impurity or information gain, which is based on entropy. Gini impurity basically measures the probability of misclassifying a randomly chosen item from a node if you just use the label distribution in that node. A lower Gini score means less impurity, more purity. So the algorithm looks for the split that results in the biggest reduction in Gini impurity. Information gain works similarly, but uses entropy, a measure of disorder. It looks for the split that gives the biggest decrease in entropy, the biggest gain in information about the target variable. For regression, predicting a number, it usually uses mean squared error, MSE. It wants splits that minimize the squared errors within the resulting nodes.
Wow, okay, so it's constantly calculating these metrics for all possible splits and picking the winner at each step.
Exactly. It does this recursively. It splits, then it looks at the resulting subgroups and splits them again, using the best feature and best cut point for that subgroup. And it keeps going until some stopping condition is met, Maybe the tree reaches a certain depth, or a node has too few samples to split further, or splitting doesn't really improve the purity much anymore.
So it builds this whole branching structure based purely on optimizing those statistical measures at each step. It's like a really efficient sorting machine.
That's a great way to put it, an efficient, data-driven sorting machine.
Okay, so beyond how it works, what are the big selling points? Why use a decision tree? I hear interpretability mentioned a lot.
Absolutely. That's probably the number one advantage. Interpretability. They're often called white box models for this reason. You can literally follow the path a single decision takes, from the root node, asking the first question, down through the branches based on the answers, all the way to the final leaf node prediction. This transparency is just invaluable.
Can you give an example?
Sure. Imagine a bank using one for loan applications. If an application is denied, the tree can tell you exactly why. Denied because credit score 650, NE, debt to income 40%, and D, recent late payments too. You see the explicit rules. It's not a mystery. This contrasts sharply with, say, a complex neural network, which might give you an answer, but struggle to explain the why in such a clear, rule-based way. We often call those black boxes.
Right, the black box problem. So this white box nature is crucial for trust, for regulations.
Yeah.
Like GDPR's right to explanation.
Exactly. It's huge for accountability, for debugging, for building user trust, and for meeting regulatory requirements. It feels like finance and healthcare. Being able to explain decisions is often non-negotiable. It really helps democratize the process, making it understandable.
Makes sense. Are there other key strengths besides being easy to understand?
Yes, another major one is their flexibility, stemming from their non-parametric nature.
Non-parametric. What does that mean compared to, say, linear regression?
Good contrast. Linear regression is parametric. It assumes a specific functional form, a straight-line relationship between inputs and outputs. It has fixed parameters, the slope and the intercept. Decision trees are non-parametric. They don't make strong assumptions about the shape of the data or the relationship between variables. The structure of the tree itself adapts to the data. The number of parameters, the splits, the nodes isn't fixed. It grows based on the data's complexity.
So it doesn't try to force the data into a predefined shape, like a line.
Precisely. This allows them to capture very complex, non-linear relationships and interactions between features. They can create these intricate decision boundaries that might be impossible for a simple linear model to find. They carve up the feature space in a very flexible, data-driven way. This makes them really good at handling real-world, messy data where relationships aren't always simple or linear.
That's fascinating. So they're interpretable and flexible enough to handle complex patterns without needing us to guess the right formula beforehand.
Exactly. That combination is really powerful. Adaptability without sacrificing transparency, at least for a single tree.
Okay, a single decision tree is pretty cool. Very understandable. But I sense a but coming. They have limitations, right? Like maybe being a bit unstable.
That's right. A single tree can be quite sensitive to small changes in the training data. A slight variation might lead to a completely different structure. They can also easily overfit, especially if you let them grow very deep. They might learn the noise in the data, not just the signal. So while interpretable, a single tree isn't always the most accurate or robust model on its own.
Right. So if one tree isn't perfect, maybe use lots of them.
Yeah.
Is that where ensemble learning comes in?
You've got it. That's precisely the idea behind ensemble learning. Strength in numbers. It's the strategy of combining predictions from multiple individual models, often these weak learners like simple decision trees, to create a much more powerful, strong learner.
The wisdom of the crowd applied to machine learning models.
Exactly. The core idea is that the collective judgment of many diverse, perhaps simpler models can often outperform any single highly complex model. Think of it like asking many different experts for their opinion versus relying on just one genius. The group is often more reliable.
Okay, I get the concept. But why does it work so well? How does averaging or voting actually make the predictions better? Is it just canceling out errors?
That's a huge part of it. Ensemble methods are brilliant at tackling the bias-variance trade-off, which is central to model performance. Firstly, they significantly reduce variance. As we said, individual trees can overfit learned noise specific to their training sample. By building many trees on slightly different data subsets, we'll get to how, and averaging their predictions, those random errors, those idiosyncrasies of each tree tend to cancel each other out. It smooths the prediction, making it more stable and less sensitive to the specific training set noise.
So averaging washes out the individual mistakes, leading to better generalization.
Precisely. And secondly, Ensembles can also reduce bias, although this is more the focus of techniques like boosting. Sometimes a single model, especially a weak one kept deliberately simple, might be too basic to capture the underlying pattern, underfitting. It has high bias. By combining multiple models, particularly in a sequential way like boosting, the ensemble can collectively capture more complex patterns than any single weak learner could alone, reducing overall bias.
So it's like finding that sweet spot, reducing the tendency to overfit variance,
Yeah,
and potentially also reducing the tendency to underfit bias.
exactly. The goal is a better balance. The combination generally leads to more accurate, more robust predictions that hold up better on new, unseen data. It leverages multiple perspectives while mitigating individual weaknesses.
Okay, let's get into the specifics. One of the most famous ensemble techniques is bagging. Sounds like groceries, but I assume it's more technical.
It is, though the name is actually quite descriptive. Bagging stands for bootstrap aggregating. And that tells you the two key steps. First, bootstrapping. This involves creating multiple different training datasets from the original one. How? By sampling with replacement.
Sampling with replacement. Remind me what that means again.
It means when you pick a data point from the original dataset to include in your new subset, you put it back into the pool before picking the next one. So a single data point might end up being selected multiple times for one bootstrap sample, while another point might not be selected at all. You repeat this process many times, creating lots of these bootstrap samples, each one slightly different but drawn from the same original data distribution.
Okay, so each sample is like a slightly varied version of the original data. Then what?
Then comes the aggregating part. You train a separate model, usually the same type of model, like a decision tree independently on each of these bootstrap samples, in parallel. So you end up with many trees, each trained on a slightly different view of the data. Finally, to make a prediction for a new data point, you aggregate the predictions from all these individual trees. For classification, you typically take a majority vote. For regression, you usually average their predictions.
So train lots of trees on slightly different data. Then let them vote or average. Simple concept, but powerful.
Very powerful, particularly for reducing variance. This idea was introduced by Leo Breiman back in 1996, and it's foundational. And the most famous example of bagging is random forests.
Right, random forests. They take bagging a step further, don't they?
They do. Random forests use the same bootstrapping idea training trees on different data samples, but they add another layer of randomness to make the trees even more diverse and less correlated with each other. When building each tree, at each split point, the algorithm doesn't consider all the available features to find the best split. Instead, it randomly selects only a subset of the features.
So not only is the data slightly different for each tree, but the available choices for splitting are also different at each step.
Exactly. This feature subsampling prevents a few very strong predictor variables from dominating the structure of all the trees in the forest. It forces the trees to explore other, potentially less obvious features, making them more diverse. This increased diversity through both data sampling and feature sampling is key to why random forests often perform so well. They're less likely to all make the same mistakes.
Like having detectives who not only see slightly different crime scenes, but are also forced to focus on different types of clues. What are the big benefits for the user?
Well, the main benefit is significantly reduced variance and thus less overfitting, leading to more robust and reliable predictions on unseen data. That's huge. Another cool benefit is out-of-bag, OOB, error estimation. Remember how each tree is trained on a bootstrap sample. That means, for any given tree, roughly 1/3 of the original data points were not included in its training sample. These are the out-of-bag samples for that tree. You can use these OOB samples to get an estimate of the forest's performance on unseen data without needing a separate validation set. It's like getting cross-validation for free during training.
Oh, that's clever. A built-in performance check. Anything else?
Yes. They also provide feature importance measures. By looking at how much each feature contributes to reducing impurity, like Gini reduction, across all the splits and all the trees, the forest can rank the features. It tells you which input variables were most useful for making predictions. This gives you some insight into the driving factors, a form of global interpretability.
Okay, so random forests. Bagging plus feature randomness leads to lower variance, free validation with OOB, and feature insights. Pretty compelling.
Definitely. They are a very popular and effective off-the-shelf algorithm for many problems.
Now, if bagging and random forests are like a committee of independent experts voting, you mentioned boosting is different, more like a team learning sequentially.
That's a great analogy. Boosting is sequential. Unlike bagging, where trees are built independently and in parallel, Boosting builds trees one after another iteratively, and the key idea is that each new tree focuses on correcting the mistakes made by the ensemble of trees built so far.
Correcting mistakes. How does that work? Does it, like, give more weight to the data points that were misclassified?
That's exactly the intuition behind early boosting algorithms like AdaBoost. It would increase the weights of misclassified examples so the next learner would pay more attention to them. Modern methods like gradient tree boosting generalize this idea using gradients of a loss function.
Okay, gradient tree boosting. That sounds important. Can you walk us through the steps? It sounds more complex than bagging.
It is a bit more involved, but the logic is really elegant. It's foundational for things like XGBoost, LightGBM, the heavy hitters. So step one, initialization. You start with a very simple initial prediction, often just a constant value, like the overall average of the target variable, a baseline guess. Step two, iterative refinement. This repeats for a set number of iterations, say m times, where m is the number of trees you want. In each iteration m, first you compute residuals. For every data point, you calculate something called a pseudo-residual. Think of it as the error or mistake the current ensemble M1 trees is making on that data point. More technically, it's the negative gradient of the loss function evaluated at the current prediction. It tells you the direction and magnitude of the error.
So the residuals is basically telling the next tree, here's what we got wrong for this data point, try to fix it.
Exactly. It's the target for the next tree. So second, you fit a new tree to residuals, you train a new decision tree, usually a shallow one, a weak learner, but you train it to predict these pseudo-residuals, not the original target values. This tree learns to predict the errors of the current ensemble. Its leaf nodes, RJM, identify regions in the data where the ensemble was making similar errors.
Okay, so the tree becomes an error prediction specialist for different parts of the data. Then what?
Third, you calculate optimal step size. For each leaf node of this new error-predicting tree, you calculate an optimal value. This value represents the best contribution this leaf should make to update the overall prediction for the data points falling into it, aiming to minimize the overall loss. And finally, fourth, you update the model. You add this new error-correcting tree, scaled by its optimal step sizes, to the existing ensemble. So FMX, the model after M trees, equals FM1X, the previous model, plus the contribution from this new tree. It incrementally improves by adding these targeted error corrections.
Wow. So it builds the model piece by piece, with each new piece specifically designed to fix the remaining weaknesses of the previous pieces.
Precisely. After M iterations, the final output is the sum of the initial prediction and all M trees. It's a highly refined model built by systematically learning from mistakes.
That sounds incredibly powerful, but maybe also prone to overfitting if you just keep correcting errors indefinitely?
Absolutely, that's a key concern, which is why tuning parameters and shrinkage are critical. You need to control M, the number of trees, too many, and you overfit. You also control the complexity of each individual tree, JM, often keeping them quite shallow. And crucially, there's shrinkage, often called the learning rate. This is a small factor, like 0.1 or 0.01, that scales down the contribution of each new tree you add.
Ah, so instead of adding the full correction suggested by the new tree, you only add a small fraction of it.
Exactly. It makes the learning process more gradual, more cautious. It prevents a single tree from having too much influence and helps the model generalize better by taking smaller steps towards the minimum error. It's very similar to learning rates in neural networks.
Okay, that makes sense for controlling overfitting. Now, I've also heard about L1 and L2 penalties in boosting, especially with XGBoost. How do they fit in? Is that more regularization?
Yes, exactly. That's another layer of sophistication, particularly in modern libraries like XGBoost and LightGBM. They incorporate L1 lasso and L2 ridge regularization directly into the tree building process, often when evaluating splits or calculating leaf values. Regularization adds a penalty term to the objective function that discourages model complexity.
Right, discourage complexity to prevent overfitting. How do L1 and L2 differ in what they discourage?
L1 regularization adds a penalty proportional to the absolute value of the coefficients, or leaf values in trees. Its key characteristic is that it tends to shrink some coefficients exactly to zero. This makes it great for feature selection, especially in sparse situations where you believe many input features are actually irrelevant. L1 helps the model focus only on the important ones.
So L1 is like a declutterer, throwing out useless features.
Kind of, yes. L2 regularization, on the other hand, adds a penalty proportional to the square of the coefficients. It shrinks coefficients towards zero, but rarely makes them exactly zero. It prefers solutions where many features contribute a little bit rather than a few features contributing a lot. It's good when you think most features have some relevance, maybe following a more dense distribution.
Okay, so L1 for sparsity and feature selection, L2 for shrinking everything gently when those features matter.
That's the general idea. And libraries like XGBoost often allow you to use a combination of both L1 and L2. This built-in regularization is a major reason why these advanced boosting algorithms are so robust against overfitting and perform so well across a wide range of problems, especially on structured tabular data. They manage complexity very effectively.
Right, tabular data. That brings us to the big comparison. We've got these powerful, interpretable to varying degrees ensemble methods. Then we have the giant in the room, deep learning. How do decision tree ensembles really stack up against the deep learning revolution? Do they still have a fighting chance, or are they becoming niche?
Oh, they absolutely still have a fighting chance. And in many areas, they're still the preferred tool. It's not really an either situation. While deep learning has undeniably achieved incredible things and grabbed the headlines, think AlphaGo's victory in 2016, that really supercharged the AI excitement. Ensemble methods, particularly gradient boosting, remain highly competitive.
Okay, but deep learning successes are hard to ignore. It seems to thrive on massive amounts of data, right?
That's true. Deep learning models often need much more data than humans to reach peak performance. But when trained on that big data, especially unstructured data like images, text, audio, they can outperform humans by far on specific tasks. Think image recognition, language translation. They excel at finding those correlations between obscure features, too subtle or complex for we humans to comprehend.
Like in computer vision with ImageNet, the error rates just plummeted.
Exactly. Computer vision saw a revolution with CNNs. ImageNet errors went from 26% down to Hinton's 15% in 2012 with AlexNet, then below human levels around 2–3% just a few years later with deeper networks like ResNet. It was astounding progress. And in natural language processing, transformers, invented by Google in 2017, were another game changer. They handle long-range dependencies in text much better. Models like GPT-3, with its 175 billion parameters, showed emergent abilities, performing tasks they weren't explicitly trained for, sometimes with just a few examples or none at all, zero-shot or few-shot learning.
So deep learning's strength seems to be uncovering these incredibly complex hierarchical patterns in massive, unstructured data sets.
That's a very good summary. Deeper networks can learn these representations efficiently, though they can be harder to optimize and train, needing lots of data, compute power, and careful preprocessing.
Okay, given all that, where do decision tree ensembles still shine? Why aren't they just obsolete for serious work?
Well, first, direct competition on tabular data. This is key. For the kind of structured tabular data, think spreadsheets, database tables that dominates business analytics, finance, healthcare records, scientific measurements. Gradient boosting methods like XGBoost, LightGBM, CatBoost very frequently outperform deep learning models, or at least they're highly competitive, often achieving state-of-the-art results with less effort. Deep learning hasn't shown the same consistent dominance on tabular data as it has on images or text.
Really, outperform deep learning on the most common type of business data. Why is that?
It's not fully understood, but potential reasons include how tree ensembles naturally handle mixed data types, numerical, categorical, how they model interactions, and perhaps they just hit a sweet spot of complexity suitable for many tabular problems without needing the vast parameter space of deep nets. Plus, there's the huge advantage of interpretability.
Ah, yes, back to the white box versus black box.
Exactly. Even with complex ensembles, you can often get feature importances, maybe use tools like SHAP to understand individual predictions better than you can with a giant neural network. This transparency is critical in regulated industries or high-stakes decisions where you need to know why the model decided what it did. It's crucial for trust, accountability, and ethical deployment. Ensembles help democratize ML by keeping it somewhat understandable.
So better performance often on common data types, and you can understand them better. That's a strong combination. What else?
Efficiency and practicality. This is huge. Deep learning often requires massive data and compute resources. Training big models can cost millions, needing specialized hardware like GPUs or TPUs. Ensemble methods, especially tree-based ones, often train much faster, work well on standard CPUs, require less memory, and can achieve excellent results with significantly less data. This makes them far more accessible and cost-effective for many organizations. You can often build a great XGBoost model on your laptop.
Lower barrier to entry, basically. Less data needed, less compute needed.
Right. And also, optimization and pre-processing tend to be simpler. Deep learning often needs careful input scaling, normalization, complex architectures, and lots of hyperparameter tuning. Tree ensembles are generally more robust to feature scaling, handle categorical features directly, especially models like LightGBM and XGBoost, and might require less intricate tuning to get good results. They're often quicker to get up and running.
It sounds like deep learning is trying to bridge that efficiency gap, though, with techniques you mentioned earlier.
Exactly. The deep learning community is very aware of these practical limitations and is working hard on efficiency. Techniques like quantization, reducing the precision of the numbers used in the network from, say, 32-bit floats to 8-bit integers, make models much smaller and faster for inference, especially on mobile or edge devices. And knowledge distillation, where you train a smaller student model to mimic a large, complex teacher model that allows you to capture much the performance of a giant research model in a smaller, deployable student model. Think DistillBERT being much smaller than BERT, but retaining most of its capability.
So deep learning is learning tricks to become more practical, kind of like ensembles already are in some ways.
Precisely. It shows that efficiency, interpretability, and practicality matter greatly, and these are areas where decision tree ensembles often have a natural advantage. So you have deep learning pushing the boundaries on perception tasks with unstructured data, and ensembles remaining incredibly powerful, efficient, and interpretable workhorses for structured data. They coexist and complement each other.
Wow, what a journey, seriously, from the simple elegance of just one decision tree.
Mhm.
Seeing how ensemble methods like bagging and boosting turn these potentially weak individual learners into really powerful, robust prediction machines, it's fantastic. And it's truly fascinating how these techniques really continue to hold their own, right? Even in this age, totally dominated by deep learning headlines, it shows simplicity combined intelligently is incredibly powerful.
Indeed. Yeah, this deep dive really underscores that in AI, there's rarely a single best algorithm for everything. It's about trade-offs. Each approach has its strengths. Decision tree ensembles offer this compelling mix of interpretability, efficiency, and strong predictive power. That makes them just indispensable tools, sitting right alongside the more data-hungry, often more opaque deep learning models. They really did help democratize machine learning, making powerful techniques practical and understandable for a much wider audience.
So whether you're out there building the next great AI app, or maybe just analyzing complex business data, or even just trying to make sense of the AI system shaping our world, it's worth remembering that sometimes the clearest path, the most reliable insight, isn't found in the most complex black box solution, but maybe in that intelligent combination of simpler, well-understood parts. It's a great lesson in how these different AI paradigms really complement each other. It's not a competition where one has to eliminate the other.
Absolutely. And that actually brings up a really important question, perhaps for you, our learner, to think about. Given these inherent trade-offs we've discussed, the interpretability and efficiency of ensembles versus the raw pattern-finding power, often with less transparency, of deep learning, how should we, as a society, as practitioners, navigate these choices? How do we decide when to prioritize one approach over the other, especially in applications with really significant real-world impact, think healthcare, finance, justice, where understanding the why might be just as critical, if not more so, than just the prediction itself? Where do we draw that line?